This lecture is about non-abelian groups, and there are two classes. So the first class are matrix groups. So let me recall what a matrix is. An M by N matrix is a rectangular array of numbers. So the first column would be, let's say, A11, A21, A31 down to AM1. Second column, A12, A22, A32 down to AM2, and so forth. And the final column, the nth column, is A1N, A2N, A3N down to AMN. And the numbers in this matrix are called the coordinates. So the coordinates may be integers, rationals, real numbers, complex numbers, any kind of numbers you choose. It's called this matrix A, and we simply denote it usually just Aij in parentheses. That's an M by N matrix. So for example, 1, 2, 3, 4, 5, 6, this is a 2 by 3 matrix. And I don't know, 0, -5, 7, 2, -3, -8 is another 2 by 2 matrix. And when you have two matrices of the same shape, that is the same number of rows and the same number of columns, you can add them. And you add just by adding coordinates. So for example, in the second row, first column, 4, 2, add to 6, 5 -3, 6 -8. So this is the rule for addition of matrices. And for fixed M and N are positive integers. The set, I'll write a capital M sub Mn of all M by N matrices is an additive abelian group. You cannot add matrices that have different shapes. You can't add a 2 by 3 matrix to a 2 by 7 matrix or a 5 by 19 matrix. Two matrices have to have the same number of rows and the same number of columns to be added, and then you can do it. Now, we also often specify what the coordinates can be. So for example, M sub Mn, if I wrote R, this would be all M by N matrices with all the coordinates Aij in the set of real numbers. Or you could look at matrices with rational coordinates or integer coordinates or complex coordinates. But this is a nice example of an additive abelian group. You can also multiply matrices. And that's important. If you haven't seen it before, you really need to look up something about matrix multiplication and learn it. Matrix multiplication. So you cannot necessarily, in fact, almost never, multiply two matrices that have the same shape. You cannot multiply a 2 by 3 matrix with a 2 by 3 matrix. When you can do matrix multiplication, it's in the following case. Suppose we have an M by N matrix. So we have M rows and N columns. And suppose we have a matrix which has, m rows and n columns. Let me just draw it like this. Sorry, this is right. M rows and n columns. And here we have an n by r matrix. So this matrix has n rows and r columns. So in every row, you have, in the matrix on the left, you have n numbers. In every column on the matrix on the right, you have n numbers. And you can multiply matrices where the number of rows of the matrix on the left equals, sorry, the number of columns on the matrix on the left equals the number of rows in the matrix on the right, and the product will be an M by R matrix. So the sort of the mnemonic to recognize what kind of matrices you get when you multiply two matrices. If you have an M by N matrix and you multiply it by an N by R matrix, you get, it's like the N's cancel, an M by R matrix. And the rule for matrix multiplication is the following. So if A is Aij, this is M by N, and B, I'll write this as Bij, N by R. So if you take the mth row of A, so this is if you take the ith row of A, it looks like this: AI1, AI2, AIN. That's the ith row of A. If you take the jth column of B, that looks like B1J, B2J, down to BNJ. And if you multiply the ith row of A by the jth row of B, so I'm going to say that A times B is the matrix C, which has coordinates Cij. So the coordinate Cij is what you get by multiplying sort of term-wise the coordinates of this row and this column and adding. So we would say summation K goes from 1 up to N, AIK, BKJ. For I going from 1 up to M, and J going from 1 up to R. So the best way to see this, if you're not familiar with it, is just to compute an example. So suppose A is a 3 by 2 matrix. I'll make it 1, 2, 3, 4, 5, 6. 3 rows, 2 columns. Suppose B is it has to have the same number of rows as this matrix has columns. So I'll make it a 2 by 3 matrix. I'll just make up some numbers. 7 minus 1, 0, 2 minus 2, 5. And so when I multiply them, AB equals C, this is going to be a 3 by 3 matrix. So what is that matrix? Cij. So C11, you take the first row, 1, 2, times the first column, you get 1 times 7 plus 2 times 2 equals 11. First row, second column, C12 is minus 1 minus 4 minus 5. First row, third column is 0 plus 10 is 10. So in this 3 by 3 matrix, The first row is 11 minus 5, 10. Second row, you take the second row into the first column. 21 plus 8 is 29. Minus 3 minus 8 is minus 11 and 20. Third row, first column, 35 and 12 is 47. Minus 5 minus 12 is minus 17, 30. So hopefully I did this correctly. And you need to check that this is the way you can multiply matrices. What are some properties of matrix multiplication? In general, if you have A is an M by N matrix, B is an N by R matrix, and C is, let's say, an R by S matrix, AB is M by R, so AB times C, this is M by R, R by S, this is M by S. If you take BC, that's an N by S matrix, and A times BC is an M by S matrix. And for all matrix multiplication, you have associativity. AB times C is A times BC. And we're going to consider a simple case. Suppose we consider 2 by 2 matrices. So A is, let's say, A, B, C, D. So you can always multiply 2 by 2 matrices because they have the same number of rows and columns. And when you multiply matrices, so 2 by 2 matrices can always be multiplied. You have the same coordinates for the matrices, the reals or complexes. So if A is A, B, C, D, and B is E, F, G, H, AB, when you multiply them, A, B, C, D, E, F, G, H, this is AE plus BG, AF plus BH, CE plus DG, CF plus DH. That's matrix multiplication, and it's associative. If you take the matrix 1, 0, 0, 1, this is called the identity matrix. And it's called the identity matrix because AI equals IA equals A for all matrices A. So if you look at these 2 by 2 matrices, there's a multiplication, a binary operation of multiplication. It's associative, there's an identity. Do they form groups? Well, they form groups if you have a multiplicative inverse. So for any matrix, 2 by 2 matrix, the determinant of A is DET of A. If A is A, B, C, D, is AD minus BC. So if the determinant of A is different from 0, suppose we let B be the matrix so that AD minus BC, let me just call it delta so I don't have to keep writing AD minus BC. D over delta minus B over delta, I can divide by delta, minus C over delta, A over delta. So, let's say we're looking at matrices with real coordinates. Actually, why is this a good matrix? Well, let's compute AB, ABCD, D over delta minus B over delta minus C over delta, A over delta. I get AD minus BC over delta minus AB plus AB over delta, CD minus CD over delta, minus BC plus AD over delta. AD minus BC is delta. This is delta over delta, that's 1. Minus AB plus AB is 0, CD minus CD is 0, AD minus BC is delta. So if you multiply A on the right by B, you get the identity. And it's also true, you should check, that B times A is the identity. So if this determinant, well, what really is, I really should say, to be careful, it has an inverse. If it's real numbers, the determinant is non-zero. We have an inverse. So what that tells us is that, let's take a nice example. Let GL2 of R be the set of 2 by 2 matrices with real coordinates and determinant not 0. This is a group because we can multiply 2 by 2 matrices. The multiplication is associative. The identity matrix is the multiplicative identity, and every matrix has an inverse. Is it an abelian group? I don't know. Let's take a sort of a random example. 1, 2, 3, 4. I don't know. I'll just make up some numbers. Minus 2, 0, 3, 5. So if I multiply these, I get minus 2 plus 6, 10, 6, 20. If I multiply them in the opposite order, minus 2, 0, 3, 5 times 1, 2, 3, 4, I get minus 2, minus 4, 18, 26. These two matrices are different. So if I were to call this A and this B, AB is this, BA is something different. So AB is different from BA. So GL2 of R is a non-abelian group. So this is important. If you look at all 2 by 2 matrices with real coordinates, that is a non-abelian multiplicative group. Now, sitting inside this group is a very important subgroup called SL2R. And there's an exercise to prove, actually I think it's in the notes, that if you have 2 by 2 matrices and you take their product, the determinant of the product is the determinant of A times the determinant of B. So if determinant of A and determinant of B are both equal to 1, then the determinant of AB is the product of the determinants. 1 times 1 is also 1. So suppose we let SL2R be the set of all 2 by 2 matrices in GL2R. This is all 2 by 2 matrices with non-zero determinant. SL2R is a subset of them, all 2 by 2 matrices in GL2R with matrices A, with the determinant of A equal to 1. So we just proved that the product of 2 matrices of determinant 1 also has determinant 1. So SL2R is a subgroup of GL2R. Sitting inside SL2R, there's another very important group. So SL2Z, this is all 2 by 2 matrices A with integer coordinates. Coordinates in Z, and determinant of A equals 1. So for example, seven, 5, 4, 3, the determinant is 7 times 3. Determinant of A is 7 times 3 minus 4 times 5. 21 minus 20 is 1. This is an element of SL2Z. And because the determinant is 1, there's a very easy formula for the matrix. So in general, if A is A, B, C, D, and the determinant of A, which is AD minus BC, is 1, then A inverse is D minus B minus C, A. You can check. So for example, for this matrix, the inverse, you interchange the diagonal elements and you change the sign of the off diagonal elements. This matrix also is determinant 1. And you multiply those two together and you get the identity. So SL2, and the identity has integer coordinates. I, 1, 0, 0, 1, has integer coordinates in determinant 1. So the set SL2Z is closed under multiplication. It contains the identity, and it contains the inverse of each of its elements. So SL2Z is a subgroup of SL2R. This is a very important, these are all very important groups. Let me give one more example of a matrix group, which is very important, certainly in not just in mathematics, but also in physics. And this is something called the Heisenberg group. So if you studied some physics, you know there's something called the Heisenberg uncertainty principle. And it's the same Heisenberg whose name is on this group. I'll call it H is going to be a group of 3 by 3 matrices. And I'm just going to look at the ones with integer coordinates. So this is all 3 by 3 matrices with the following properties. Down the main diagonal, there are ones. Under the main diagonal are zeros, so that leaves 3 places. So I'll call this coordinate A, this coordinate B, and this coordinate C. So H3 of Z, this Heisenberg group, is all 3 by 3 matrices where A, B, C are integers. So let me first of all prove this is a group. So suppose I take 2 elements. Let me just call them X and Y. Say X is the matrix 1, that matrix. Write it a little bit better. And let's say Y is the matrix D, E, F. And let's say I take another matrix Z. Well, I don't need Z. We know matrix multiplication is always associative. But let's just show that this set of matrices is closed under multiplication. So what is X times Y? 1AC, 0, 1B, 0, 0, 1. This is the way I've written it. Times the matrix 1, 0, 0, D, 1, 0, F, E, 1. So the first coordinate is 1. Let me compute the first column. So first row into the first column is 1. Second row is 0. Third row is 0. What about the second column? First row into the second column gives A plus D, which is an integer. 1, 0. First row into the third column gives F plus AE plus C. Second row, third column is B plus E. Third row, first column is a 1. Perfect. So if you look at this product, I have 1s down the diagonal, 0s below the diagonal, and integers in the upper triangular corner of the matrix. So H three of Z is closed under multiplication, and the identity matrix, now we have to look at the 3 by 3 identity matrix. Well, this has 1s down the diagonal and 0s below, so this is an H3 of Z. So this contains the identity. We just need to show that it contains the inverse of each of its elements. That is, if you take a matrix of this form, the inverse also is of this form. So if X is 1, A, B, C, 1, 1, 0, 0, 0, suppose we let Y, so I want something where X times Y is the identity. So I'm given A, B, and C. This is the product. I need a 0 here. So what has to go into the D place is minus A. I need a 0 here, so E has to be minus B. And I want this to be 0. That is, I need F plus AE plus C equals 0. So I know that F, I need to find F. I know that E, where is E? E is this coordinate. E is equal to minus B. So F minus AB plus C equals 0. So F has to equal AB minus C. So I put AB minus C here. And now you have to check that if you multiply these two matrices, x, y is the identity. So y equals x inverse, and H3 of Z is a group. It's a very important group. Everything's very important. Yeah. Yeah. So that's our last example for the morning of a matrix group. So we've actually seen 4 matrix groups. GL2R, 2 by 2 matrices with real coefficients and non-zero determinant. SL2R, 2 by 2 matrices with real coefficients and determinant 1. And SL2Z, which are 2 by 2 matrices with integer coefficients and determinant 1. And this group of 3 by 3 matrices, the Heisenberg group, which has this very special form. In the next talk, we'll give the second class of non-abelian groups, which are permutation groups.